this tiny device supposed to replace GPS? And why is it on board NASA's secretive space plane?
We have liftoff.
Headed for a test run in space. It's called a quantum inertial sensor, or quantum GPS. But how it works is both fascinating and slightly mind-bending. Because instead of listening to satellites, this sensor watches ultra-cold atoms. Lasers split these atoms apart and brings them back together. And the way they interfere tells the system how it's moving. Think of it as motion tracking at the atomic level. Normally, GPS needs about 4 satellites to tell you where you are. But here's the problem. GPS can be jammed, spoofed, or shut down, especially in conflict zones. In fact, over 1,000 flights per day are affected by GPS denial. So instead of listening to satellites talking to you from space, this sensor knows exactly where it is on its own, even when GPS goes dark. A similar system was tested on Earth and it actually outperformed GPS, earning a spot on Time's Best Innovations of 2025. Right now, companies are focusing on government and enterprise use first, but next it's aviation, shipping, and autonomous vehicles. And this tech has serious implications. It could keep navigation working in GPS-denied environments, allow exploration on Mars, the Moon, and deep space, and redefine how vehicles move without external guidance. It's not surprising why countries like the US, China, and UK are heavily investing in. So yes, this will change the world. But here's Bob. Bob doesn't think there's much to look forward to anymore. All he sees is talks of war, climate collapse, and things falling apart. So let's see if the next 6 innovations cannot just change the future, but Bob's mind. First, imagine flying from London to New York in under 3 hours. Because right now, that same flight can take up to 8. And the reason why it got that fast was supersonic aircraft, like Concorde, one of the world's first commercial supersonic flying passenger planes. It crossed the Atlantic in under 3 hours. Despite being a technological triumph, it never could work long term. It burned massive amounts of fuel, it was extremely expensive to operate, and the sonic booms rattled cities. And after a tragic collapse in the 2000s, confidence collapsed. So Concorde was grounded, with the supersonic travel disappeared. But now, it's back. Companies like Boom Supersonic have already tested aircraft that break the sound barrier. And they're planning on designing planes that aim to fly faster and more efficiently than the Concorde ever could. At the same time, NASA and Lockheed Martin are testing a very different idea. Instead of a deafening boom, they're trying to turn it into a quiet thump. If that works, it could lift the ban on supersonic flight over land, the very rule that grounded the Concorde. And if these new designs succeed, you could fly in a supersonic jet by 2030. Now, Bob's worried about AI because AI has massive demands for power. By the end of this decade, AI will consume about 4% of the world's electricity supply. That's roughly the same as Japan's entire annual energy usage. But how much of that is actually clean energy? Right now, only about 20% of the electricity powering AI and data centers comes from renewable sources. And some analysts suggest that it could reach 50% by 2030. And the renewable scaling the fastest, solar. And it just got a major upgrade. Perovskite. It's a crystal structure that's exceptionally good at capturing sunlight and turning it into electricity. When used in solar panels, it can dramatically boost efficiency. Perovskites don't just replace silicon, they can be tacked on top of silicon to form tandem panels. That pushes efficiency far beyond what silicon alone can achieve. And perovskite panels are cheaper to produce, but they have a problem: durability. Long-term stability has held them back, but researchers are rapidly improving on this. Because perovskite could make solar energy cheaper, more efficient, and usable in places silicon can't go. From curved surfaces to lightweight rooftops, even vehicles. In fact, companies like Oxford PV have already shipped some of the world's first perovskite tandem solar panels. But as we generate more electricity, how we store it has to evolve. It has to be able to hold more power, charge faster, be far more reliable. And that's why we need solid-state batteries. Because they replace the liquid electrolyte inside today's lithium-ion batteries with a solid material that moves ions between electrodes. But that single change unlocks a lot. First, safety. No flammable liquid means a reduction in fire risk and thermostability. Second, energy density. More electrodes can be packed in a tight space, meaning more range, without increasing the space. Third, charging speed. Many estimates suggest that EVs with solid-state batteries can charge 2 to 6 times faster. That means recharging your EV in about the same time it takes to refuel your tank. Fourth, longevity. They degrade more slowly, give better charging cycles, and therefore longer lifespan. Fifth, temperature resilience. They can operate in both cold and hot environments. All of this is exactly what EVs need: longer range, faster charging, and safe and more reliable batteries. And it finally looks achievable. Toyota, one of the longest standing leaders in this space, is planning to release an EV with a solid-state battery between 2027 and 2028. But here's the catch: these batteries still face cost and manufacturing challenges, which is why they're arriving gradually and not replacing lithium-ion overnight. And then there's this: AI is slowly becoming part of your doctor's office, and that really stresses Bob out, because AI hallucinates, not in a human sense, but in a far more dangerous way.
Researchers have found that it sometimes invents text. It's what's known in the industry as hallucinations.
AI hallucinations happen where a system creates information that sounds confident and correct, but is actually wrong, incomplete, or fabricated. It's not lying, it's predicting what should come next based on patterns it learned, even when the truth isn't there. And in healthcare, that's a big problem. AI hallucinations have shown up in transcription tools that invent words or diagnostics that were never said before, diagnostic support systems that mislabel anatomy or disease, medical chatbots and summarization tools that insert false information inside patient records or test summaries. So yeah, it's easy to see why Bob wouldn't immediately trust AI inside a hospital. But here's the other side of the story. What has AI actually helped us improve? First, doctors' time. Roughly 45% of doctors in the US report burnout, largely driven by administrative workloads. In fact, doctors spend twice as much time on clerical tasks than on real patients. And that's where AI steps in. AI helps cut documentation time by up to 60%. And some systems report burnout reduction by up to 30%. And more than half of the doctors say that AI could help reduce stress and burnout by reducing their administrative workloads, which means doctors spend less time typing and more time treating patients. And then there's drug discovery. Traditional drug development can take a decade or more, cost billions, and still fail later on in the process. AI changes that. It can analyze massive biological datasets and reduce the time from initial idea to viable drug candidate. Selected drugs in early trials have higher success rates than traditional methods, meaning fewer failures sooner. So on one hand, AI hallucinations are a big thing. On the other, they're actively being worked on. Bob might still be cautious, but he's starting to see why this technology actually exists. Heck, it even helped produce bone glue, which does as advertised. Bob also found out something else. In the US alone, over 100,000 people on an organ transplant waiting list. More than 48,000 transplants happened in 2024. That gap has consequences. Roughly 13 people die per day because an organ didn't arrive on time. Seeing this broke Bob's heart. But there's this: Xenotransplantation. No, not a xenomorph, but the practice of transferring cells, tissue, or organs from one species to another, like from genetically modified pigs to human. This is because there isn't enough human organs to meet the demand. So researchers turn to pigs because their organs are similar in size and functionality. And modern gene editing allows scientists to reduce the chances of immune rejection. Recently, surgeons successfully transplanted a gene-edited pig kidney to a human being. And those organs worked. That was a proof of concept. However, they have real consequences. Even modified organs can still trigger strong immune rejection. There's risk of xenozoonosis, animal viruses crossing over into human, and there's serious ethical questions about animal welfare. So xenotransplantation isn't a silver bullet, but it's a bridge. But as we build that bridge, there's a middle path: 3D printed organs. 3D bioprinting uses living human cells and biomaterials to print tissues layer by layer, just like a 3D printer builds plastic objects. So far, scientists have already bioprinted simple structures like ears. And now they're working on the hardest part: printing blood vessels, the key to ensuring that those organs are fully functional. And the goal is used to create patient-specific organs that are made from patients' own cells to reduce rejection, and aim to eliminate transplant waiting lists by providing on-demand organs. These printed tissues already help out in other ways too, like testing drugs and diseases without risking human lives. But even if it works, regulations and safety trials will take years. So no, this doesn't replace organ donation tomorrow. Bob knows that. But for the first time, he also knows this: people aren't just waiting for organs anymore. They're building them. And that changes something. Because now, hope isn't about luck or waiting for tragedy to save a life. It's about engineering a future where fewer people die simply because time ran out. And for Bob, that's something worth believing in. Hey, what's that? It's a robot. And that's NVIDIA. What? Because building robots isn't supposed to be easy. Robotics is one of the hardest engineering problems on Earth. Hardware breaks, testing is expensive, and one mistake can cost millions in damages or downtime. So why are robots showing up everywhere? Traditionally, robots are trained in the real world, which means every test takes time, every crash costs money, and scaling that process can be brutally expensive. But this is where NVIDIA stepped in with Omniverse. Think of it like a realistic boot camp for robots, not for games. For training robots before they ever touch the real world or grass. Instead of testing robots in the real world, developers can now simulate warehouses, factories, and workflows digitally. It's kind of like a metaverse for robots, but this one worked out. And at the center of this is NVIDIA's Isaac Sim. Instead of months in physical training, robots can be validated or tested in a matter of days. That's why this fast-growing and soon-to-be trillion-dollar industry is moving towards software-first development. And hey, Bob is paying attention. Because this isn't just for mega corporations. It will be able to support him or his team. It handles rare edge cases that would be hard or dangerous to capture in real life. And it lets small teams do what once required massive labs. Suddenly, you don't need fancy things to train your robot. You just need a GPU. That's why companies like Amazon, Bosch, Boston Dynamics, Figure AI, and others are using Omniverse and Isaac Sim to accelerate the robotics workflows. And this is where Bob realizes something. Robots aren't taking over because they got smart overnight. They're taking over because we finally built worlds in which they can learn safely. But here's the final story, the one that shocked me the most and might make Bob finally happier and more optimistic. It's not the neighbor of your neighbor's dog, but it's a revolutionary gene editing system that allows scientists to precisely edit DNA, adding, removing, or altering specific segments of genetic sequences. CRISPR became one of the world's leading gene editing technologies because it was more precise, versatile, and easier to program than other tools. In 2023, the first CRISPR-based gene editing therapy called Casgevy was approved to treat sickle cell disease and other blood disorders caused by genetic mutations. In 2025, a child with a rare metabolic disease was successfully treated with a personalized CRISPR gene editing therapy that corrected the mutation in his liver cells and allowed his metabolism to improve, potentially avoiding a liver transplant. Also, CRISPR is being used in modern diseases like Huntington's disease, where editing has reversed symptoms in aggressive mouse models, and early human HIV gene editing trials have shown promising DNA targeting. But if CRISPR cuts the wrong DNA sequence, it can cause unintended mutations that are very harmful. The body can sometimes react to the components used to express or deliver CRISPR. Safely and efficiently bringing CRISPR to specific cells in the body is still a major hurdle. Editing human embryo is highly controversial and restricted in many countries. But are CRISPR therapies working for everyone? Not yet. Current approved therapies are mostly for conditions like blood disorders. Rare disease personalized therapies like that rare infant case are exceptionally first steps, not yet widely available. When could it be more common? Mid to late 2020s, more approved therapies for blood disorders and other conditions entering the clinic with improved delivery and reduced side effects. In the 2030s, we'll have wider applications to complex diseases like cancer, diabetes, and cardiovascular conditions as delivery systems mature. So we can rest assured that the future is something to look forward to and not fear, despite what we see.